Imagine standing at the edge of the universe. Not the edge as poets describe it, some soft, glowing boundary where stars thin out and darkness takes over, but a real, physical threshold. A place where the very fabric of space and time folds back on itself like a piece of paper being creased by invisible hands. Now imagine that on the other side of that fold, there is another point in space. Maybe it's a billion light years away. Maybe it's in a completely different universe. Maybe it's yesterday. And between those 2 points, between here and there, between now and then, there is a tunnel. A tunnel so strange, so mathematically precise, so hauntingly beautiful in its theoretical structure, that the greatest minds humanity has ever produced have spent their entire careers trying to determine whether it actually exists. That tunnel has a name. We call it a wormhole. And what you are about to discover is going to change the way you think about space, time, distance, reality, and the future of the human species. Because wormholes are not science fiction. They were never science fiction. They are science. They emerged directly from Einstein's equations. They have been studied by Nobel Prize winners, debated by the most brilliant physicists alive today, and they sit at the intersection of everything we know and everything we desperately want to understand. And there are 11 things about wormholes that most people have never heard. 11 facts so astonishing, so paradigm-shattering, so emotionally powerful that once you hear them, you will never look at the night sky the same way again. So before we begin, ask yourself this question. What if the greatest adventure in human history is not a journey to another planet, but a journey through a hole in the fabric of reality itself? The story of wormholes does not begin in a laboratory. It does not begin with a telescope pointed at a distant galaxy, or with an astronaut floating in the void of space. It begins with a piece of chalk. It begins in the early 20th century, in a world that was still reeling from the shock of discovering that the universe did not work the way anyone thought it did. For centuries, human beings had believed in a cosmos governed by Newton's laws, a universe of predictable, clockwork mechanics where space was a fixed, unchanging stage and time ticked forward at a constant, unvarying rate. Every apple fell from every tree at the same rate. Every planet moved in its orbit according to rules that could be calculated in advance. The universe was, in a word, sensible. And then along came Albert Einstein. Born in 1879 in the city of Ulm, in what is now Germany, Einstein was a young man of extraordinary intellectual restlessness. He was not, as the legend sometimes goes, a poor student. He excelled in mathematics and physics, but he was deeply resistant to authority, deeply suspicious of received wisdom, and driven by an almost pathological need to understand things from first principles. He wanted to know not just how the universe worked, but why. And in 1905, in what historians of science call his annus mirabilis, his miracle year, he published 4 papers that collectively transformed physics. One of them introduced the special theory of relativity, and it contained a sentence that would eventually lead us, step by step, through a labyrinth of mathematics and imagination, to the concept of the wormhole. That sentence, expressed in the language of equations, said this: space and time are not separate things. They are a single, unified fabric, a 4-dimensional continuum, and nothing in that continuum, no information, no particle, no wave of light, can travel faster than the speed of light. Now, at first glance, this might seem unrelated to wormholes. But follow the thread, because this is where the story gets extraordinary. If space and time are a single fabric, a fabric that Einstein called space-time, then that fabric can, in principle, be shaped. It can be bent. It can be curved. And if it can be curved, then the shortest distance between 2 points is not necessarily a straight line. It is whatever path the geometry of space-time allows. Think about that for a moment. Take a flat piece of paper. Draw a dot on the left side and a dot on the right side. The shortest distance between those 2 dots on the flat paper is a straight line. That is Euclidean geometry. That is Newton's universe. But now, fold the paper. Bring the 2 dots close together. Suddenly, the shortest distance between them is not the long line across the paper. It is the tiny gap between the two folded edges. The paper has not changed. The dots have not moved. But the geometry has changed, and that change has made the impossible possible. This is the fundamental insight behind the concept of the wormhole. And it is not a metaphor. It is mathematics. It is what Einstein's equations actually allow. Einstein published his general theory of relativity in 1915, a decade after special relativity, and it was, by any measure, one of the greatest intellectual achievements in human history. General relativity described gravity not as a force, as Newton had imagined, but as a curvature in the fabric of spacetime. Mass curves spacetime. The more mass, the more curvature. And objects moving through spacetime follow the curves. They fall toward massive objects not because they are pulled, but because the geometry of spacetime guides them there. It was a revolution. It was beautiful. And it was immediately apparent that Einstein's equations had solutions. Mathematical descriptions of possible universes that were deeply, deeply strange. One of the first solutions was found by a German physicist named Karl Schwarzschild, who was serving on the Russian front during World War I when he did the calculations. In the middle of a war, while shells were falling around him, Schwarzschild derived the exact solution to Einstein's equations for a perfectly spherical, non-rotating mass. And what he found was extraordinary. At a certain critical radius, a radius that depended on the mass of the object, something catastrophic happened to the geometry of spacetime. The fabric did not just curve. It closed in on itself. It formed a point of no return. We now call this radius the Schwarzschild radius, and the object it describes is what we call a black hole. Now, here is where the wormhole enters the picture, and here is the fact that most people have never heard, the fact that stops physicists in their tracks when they first encounter it. The mathematical solution that describes a black hole, the Schwarzschild solution, does not just describe a one-sided pit in spacetime. When you write down all the mathematics fully, when you look at the complete solution without cutting it off, what you find is that the Schwarzschild black hole has not one region of extreme spacetime curvature, but two. Two regions connected at their centers. Two separate points in spacetime, potentially in two separate universes, or two separate regions of the same universe, joined by a narrow, tube-like structure through the interior of the black hole. In other words, hidden inside the mathematics of the very first solution to Einstein's equations, there was already a wormhole. It was 1935 when Einstein himself, working with his colleague Nathan Rosen at the Institute for Advanced Study in Princeton, New Jersey, sat down and examined this double structure carefully. They realized that the Schwarzschild solution implied the existence of what they called a bridge, a geometric connection between two separate regions of spacetime. Einstein and Rosen did not know what to make of it. They were not sure if it was a mathematical artifact, a curiosity of the equations, or something that could be physically real. They published a paper about it in the journal Physical Review, and for a long time, this structure was known not as a wormhole but as an Einstein-Rosen bridge. The name wormhole came later, coined by physicist John Archibald Wheeler in 1957. Wheeler was one of the most colorful, brilliant, and influential physicists of the 20th century. A man who coined the terms black hole, quantum foam, and Ephraim bit, and who had an almost poetic gift for capturing physical concepts in memorable language. He imagined a worm eating through an apple as a metaphor for how a wormhole cuts through the fabric of spacetime, creating a shortcut between two distant points. The name stuck, and the concept, this wild, strange, mathematically legitimate idea, began its slow, tortuous journey from the margins of theoretical physics toward the center of scientific debate. But here is the thing about the original Einstein-Rosen bridge that everyone needs to understand, because it sets up one of the most important twists in this entire story. The original wormhole, the one that emerges from Schwarzschild's solution, the one that Einstein and Rosen described, is not traversable. It cannot be used as a shortcut. It cannot be used for anything at all. And the reason why is both simple and devastating. To understand why the original wormhole is not traversable, you need to understand what happens to it over time. The Schwarzschild wormhole, the Einstein-Rosen bridge, exists for only an infinitesimally brief moment. It forms, and before any object, any particle, any photon of light could possibly travel through it, it collapses. The throat of the wormhole, the narrowest point, the connection between the two regions of spacetime, pinches off. It closes like a fist clenching, and anything that tried to pass through would be caught in the collapse, crushed, destroyed. The wormhole blinks into existence and then vanishes in a span of time so short it makes a nanosecond look like an eternity. So when physicists in the mid-20th century looked at this result, many of them concluded that wormholes were indeed just mathematical curiosities. Interesting solutions to Einstein's equations, perhaps, but not physically relevant. Not something you could build a spacecraft around. And for decades, that was more or less where the conversation stood. The wormhole was acknowledged, noted, and then largely set aside. And then, in 1988, everything changed. 1988. Think about what the world looked like in 1988. The Cold War was winding down. Personal computers were becoming widespread. The Hubble Space Telescope had not yet been launched. And at the California Institute of Technology, Caltech, a physicist named Kip Thorne received an unusual request. Carl Sagan was writing a novel. You might know Carl Sagan as the host of the original Cosmos television series, or as the author of The Pale Blue Dot, or simply as one of the most eloquent scientific communicators of the 20th century. But in 1985, Sagan was writing Contact, a novel about humanity's first communication with an extraterrestrial intelligence. And in the novel, his protagonist, a scientist named Ellie Arroway, needed to travel 26 light-years to the star Vega in a matter of hours. Sagan knew that faster-than-light travel violates special relativity. He did not want to use science fiction hand-waving. He wanted to know if there was any real, mathematically legitimate way to do what he needed Ellie to do. So he called Kip Thorne. And Kip Thorne, who would go on to win the Nobel Prize in Physics in 2017 for his role in the detection of gravitational waves, sat down and thought about it seriously. And what he concluded, after months of work with his graduate students Michael Morris and Ulvi Yurtsever, was both astonishing and deeply challenging. A traversable wormhole, a wormhole stable enough and large enough for a human being to pass through, is, in principle, mathematically allowed by the equations of general relativity. It does not violate Einstein's theory. It is consistent with the known laws of physics. But there is a catch. There is always a catch. And this catch is one of the most fascinating, most debated, most mysterious things in all of modern physics. To keep a wormhole open, to prevent the throat from collapsing, you need something. Something that fills the interior of the wormhole, something that pushes outward against the gravitational tendency to collapse. And that something is not ordinary matter. It is not atoms, or molecules, or dark matter, or any of the things we are familiar with. What you need to hold a wormhole open is something called exotic matter. And exotic matter is extraordinary in its properties, because exotic matter must have negative energy density. Let that sink in. Not low energy density, not zero energy density, negative energy density. Matter that weighs less than nothing. Matter that, in some sense, has gravity working in reverse, pushing outward instead of pulling inward. Now, is this possible? Is negative energy density a real thing? Or is this the point where physics slips into fantasy? Here is where it gets genuinely remarkable. Negative energy density is real. It has been measured in a laboratory. It is not theoretical speculation. It is experimental fact. And the phenomenon responsible for it is called the Casimir effect. The Casimir effect was predicted in 1948 by the Dutch physicist Hendrik Casimir, and it emerges from one of the strangest aspects of quantum mechanics, the fact that empty space is not empty. Quantum field theory tells us that even in a perfect vacuum, the lowest energy state of any quantum field is not zero. There are fluctuations. There are virtual particles constantly popping in and out of existence, borrowing energy from the universe for the briefest instant allowed by the Heisenberg uncertainty principle, and then annihilating each other and disappearing. This quantum foam, as Wheeler called it, fills all of space. And when you place two conducting plates very close together, within fractions of a micron of each other, something interesting happens. Between the plates, the wavelengths of the virtual particles that can exist are limited by the space between the plates. Only certain wavelengths fit. But outside the plates, all wavelengths can exist. The result is that there are more virtual particles pushing inward from outside than pushing outward from inside. The plates are pushed together by the vacuum itself. And the region between the plates, that tiny gap, has a negative energy density compared to the surrounding space. This was confirmed experimentally in 1997 by Stephen Lamorrow, working at the University of Washington, who measured the Casimir force directly. So negative energy exists. The question is whether it can exist in the quantities and in the geometric configuration required to hold a wormhole open. And here is where the difficulty lies. Because the amount of exotic matter required to hold open a traversable wormhole of any useful size, large enough for a human being, say, is staggering. According to the calculations of Morris and Thorne, the amount of negative energy required would be comparable to the total energy output of an entire star, or even larger. Some calculations suggest it might need to be the equivalent of the mass energy of a planet with negative energy. This is not a small engineering challenge. This is a challenge that may be beyond the capabilities of any civilization we can currently imagine. But, and this is crucial, physics does not say it is impossible. It says it is hard. And in the history of science, hard has a way of becoming possible. Now, ask yourself this question and really sit with it. If you discovered tomorrow that wormholes were real, that traversable wormholes could be constructed, what would that mean for your life? What would that mean for the human species? What would that mean for everything you think you know about the universe and our place in it? Because this is not a thought experiment with no stakes. This is a question that real physicists are asking with real mathematical rigor. And the answers they are finding are taking us to places that are genuinely difficult to process emotionally. Because traversable wormholes do not just allow travel between distant points in space. They allow something even more astonishing. They allow travel through time. The connection between wormholes and time travel is one of the most mind-bending things in all of physics, and it deserves to be explained carefully, because it is not science fiction. It emerges directly and inevitably from the mathematics of general relativity. Here is how it works. One of the most bizarre and well-confirmed predictions of special relativity is a phenomenon called time dilation. Time dilation means that time does not pass at the same rate for all observers. The faster you move, the slower time passes for you relative to an observer who is moving more slowly. This is not a theoretical conjecture. It has been confirmed experimentally many times, using atomic clocks on airplanes, on satellites, in particle accelerators. The GPS system in your phone would not work without corrections for relativistic time dilation. The satellites moving at high speed experience time slightly differently from clocks on the ground, and if these differences were not accounted for, your GPS would accumulate errors of several kilometers per day. So time dilation is real. Now, imagine a traversable wormhole. Imagine that one mouth of the wormhole, one end of the tunnel, is accelerated to a high velocity, a significant fraction of the speed of light, and then brought back. Because of time dilation, the moving mouth of the wormhole will have aged less than the stationary mouth. When you accelerate one mouth and bring it back, you have created a situation where the two ends of the wormhole are not synchronized in time. Time passes differently at each end. And if you then step through the wormhole, you are not just traveling through space, you are traveling through time. You could exit through the wormhole at a moment in the past, or, depending on the configuration, the future. Kip Thorne, along with Morris and Yurtsever, worked through exactly this scenario in 1988 and 1989, and their conclusion was unambiguous. A traversable wormhole, if it could be created and manipulated, would inevitably function as a time machine. This is not a wild extrapolation. It is a direct consequence of the physics. And it raises a question that has haunted physicists ever since. If time machines are theoretically possible, why don't we see time travelers? Why hasn't anyone from the future come back to visit us? This is known as the grandfather paradox problem, and it is one of the deepest puzzles in all of physics. Stephen Hawking, who was perhaps the most famous theoretical physicist of the late 20th century, wrestled with this problem and proposed what he called the chronology protection conjecture. Hawking argued that the laws of physics, taken as a whole, conspire to prevent time travel, not because of some moral or philosophical principle, but because of quantum effects. Here is his argument. If a wormhole were used to send a signal, or a particle, or anything, back in time to a moment before the wormhole existed, you would create a closed time-like curve. A loop in time. And on that loop, you could send information forward in time through the wormhole and back in time through the loop, creating a feedback signal that would amplify itself indefinitely. Every time the signal passed through the wormhole, it would gain energy, building and building until it formed an infinitely powerful burst of radiation that would destroy the wormhole itself. Hawking believed that quantum vacuum fluctuations, the same Casimir effect type phenomena we discussed earlier, would be amplified around any nascent time machine until they reached an infinite energy density and tore the wormhole apart. In other words, the universe itself would sabotage any attempt to build a time machine. The wormhole would destroy itself before it could be used to travel through time. This is Hawking's chronology protection conjecture, and it has been deeply influential. But, and this is important, it is a conjecture. It has not been proven. Hawking himself described it as a speculation, a bet he was making about how the physics would turn out. And in 2020, new calculations by a group of physicists including Juan Meldacena, one of the most brilliant and influential theoretical physicists alive, began to suggest that the situation might be more complicated and more interesting than Hawking imagined. But we will come back to Meldacena, because what he discovered is one of the most extraordinary things in this entire story, and it deserves its own moment. Before we get there, let us talk about what wormholes look like. Because this is one of those aspects of the topic that science fiction has both captured and distorted, and the truth is more interesting than anything Hollywood has created. If you were somehow positioned in space near one mouth of a traversable wormhole, what would you see? This question has actually been studied carefully, using the mathematics of ray tracing through curved spacetime, and the results have been published in peer-reviewed journals and visualized in computer simulations. The most famous of these visualizations was done by the team that worked on Christopher Nolan's film Interstellar, which was produced in close collaboration with Kip Thorne. In Interstellar, the wormhole appears as a sphere, a transparent, glassy sphere floating in space near Saturn. Not a flat ring, not a spinning vortex, but a sphere. And that is actually what the physics predicts. The mouth of a wormhole would appear spherical, because the wormhole connects two regions of spacetime in all directions simultaneously. If you looked at the sphere from outside, you would see through it, but what you would see inside would not be the space behind the sphere. You would see the sky of the other side. If the wormhole connected our solar system to some location near the center of the Milky Way, you would look into the sphere and see the packed, blazing, roiling star fields of the galactic core, just hanging there in the sphere like a window into another world. The light from the other side would be distorted, bent by the extreme curvature of spacetime inside the wormhole, but it would be visible. It would be real. The appearance would also include a ring of distorted images of the surrounding space, caused by gravitational lensing, similar to but more extreme than the rings of distorted starlight seen around black holes. And if you flew into it, if you entered the wormhole, what would happen? According to the calculations of Morris and Thorne, for a wormhole with a sufficiently large throat and gentle enough tidal forces, you would feel nothing unusual as you crossed the threshold. The transition would be smooth. The geometry would change around you, but if the wormhole were large enough, the tidal forces, the differences in gravity across your body, would be too small to feel. You would simply fly through a region of extreme space-time curvature and emerge, perhaps moments later, in a completely different part of the universe. Or a different time. Or, according to some theories, a different universe entirely. And this brings us to one of the most fascinating and least discussed aspects of wormhole physics: the connection between wormholes and the multiverse. The concept of the multiverse, the idea that our universe is not the only universe, that there exist other universes, perhaps infinitely many, with different physical laws, different histories, different content, is one of the most controversial and exciting ideas in modern physics. It emerges from several different theoretical frameworks, including the many worlds interpretation of quantum mechanics, eternal inflation in cosmology, and string theory. And wormholes, in some theoretical models, can connect not just different regions of our universe but different universes entirely. Recall the original Einstein-Rosen bridge. In the full mathematical description of the Schwarzschild black hole, in what is called the maximally extended Schwarzschild solution, the two regions connected by the wormhole are not just two distant parts of the same universe. They are two entirely separate universes. Two separate space-time manifolds, joined at the throat of the black hole. This is not a metaphor or an approximation. It is what the mathematics says. Now, the maximally extended Schwarzschild solution is an idealization. It describes a black hole that has existed for an infinite amount of time, which is not physically realistic. Real black holes form from the collapse of matter, and the geometry inside them is different from the idealized case. But the theoretical possibility of interuniversal wormholes that connect separate universes, is real, and it has profound implications. It means that if wormholes are traversable, if the exotic matter problem can be solved, then travel between universes might be possible. Not just travel between galaxies, not just travel through time, but travel to entirely different realities. And at that point, the concept of the wormhole has grown from a mathematical curiosity into something that challenges our most fundamental notions of what existence means. Now, let us pause here and ask a question that might seem obvious but is actually very deep. Do wormholes actually exist? Not in the abstract mathematical sense. We have established that the equations allow them. But in physical reality, right now, somewhere in the universe, are there actual wormholes? This is one of the most active areas of debate in theoretical physics, and the honest answer is, we do not know. But there are reasons to believe they might. The first reason is black holes. We now know, with extraordinary certainty, that black holes are real. They are not mathematical fictions. They are physical objects that form, evolve, and interact with their environment in ways we can observe and measure. The first direct image of a black hole, the supermassive black hole at the center of the galaxy M87, later followed by the image of Sagittarius A star, the supermassive black hole at the center of our own Milky Way, was captured by the Event Horizon Telescope collaboration and published in 2019. These images showed exactly what General Relativity predicted: a dark central shadow surrounded by a ring of glowing, superheated plasma. Black holes are real. And if black holes are real, if the extreme space-time curvature described by Schwarzschild solution is real, then the geometry of space-time can indeed reach the extremes required for wormhole formation. The physics allows it. Whether nature actually produces it is a separate question. The second reason is quantum mechanics, and specifically a phenomenon that Juan Meldacena has spent much of his career studying. Meldacena is an Argentine-American theoretical physicist at the Institute for Advanced Study in Princeton, the same institution where Einstein worked, and in 1997, he made a discovery that changed physics. He discovered what is now called the AD-CFT correspondence, also known as the holographic principle, which showed that certain theories of quantum gravity in a higher dimensional space are mathematically equivalent to quantum field theories on the boundary of that space. In other words, he found a deep mathematical connection between gravity and quantum mechanics, two theories that had resisted unification for nearly a century. And in 2013, working with Leonard Susskind, another towering figure in theoretical physics, Meldacena proposed something that stopped the physics community in its tracks. He proposed that wormholes and quantum entanglement are not just analogous. They are the same thing. This proposal is known as ER equals EPR, and it is one of the most profound and debated ideas in contemporary physics. The name comes from two separate discoveries. ER stands for Einstein-Rosen, referring to the 1935 paper on the Einstein-Rosen bridge, the wormhole. EPR stands for Einstein-Podolsky-Rosen, referring to a different 1935 paper in which Einstein, together with Boris Podolsky and Nathan Rosen, described what Einstein called spooky action at a distance, what we now call quantum entanglement. Quantum entanglement is one of the most mysterious phenomena in all of science. When two particles are entangled, they are connected in such a way that measuring one particle instantly affects the state of the other, regardless of the distance between them. The particles can be on opposite sides of the galaxy, and the correlation is instantaneous. This does not violate special relativity, because you cannot use entanglement to transmit information faster than light. But the correlation is real, it has been measured countless times, and it defies any classical intuition about how the world works. Einstein hated it. He called it spooky action at a distance and spent years trying to show it was somehow illusory, a sign that quantum mechanics was incomplete. He was wrong. Quantum entanglement is real, but the phenomenon remained deeply mysterious. What Meldesena and Susskind proposed in 2013 was this: two entangled black holes, two black holes that share a quantum state, are connected by a wormhole. The entanglement is not just analogous to the wormhole. It is the wormhole. The geometric connection in spacetime is the same thing, expressed in different language, as the quantum correlation between the particles. ER equals EPR. Spacetime geometry equals quantum entanglement. If this is correct, and many physicists think it is, or at least that it is pointing at something very deep and very real, then wormholes are not exceptional. They are everywhere. Every pair of entangled particles in the universe might be connected by a microscopic wormhole. The fabric of spacetime might be woven out of quantum entanglement. Spacetime itself might emerge from wormholes. This is one of the most staggering ideas in the history of physics, and it is actively being pursued today by some of the best minds in the world. And this idea led to an experiment. In 2022, a team of physicists led by Maria Spiropoulou at Caltech, in collaboration with researchers at Google, MIT, Harvard, Fermilab, and other institutions, performed an experiment on Google's Sycamore quantum computer that they described as simulating a traversable wormhole. The paper was published in the journal Nature in November 2022 and immediately generated enormous excitement and controversy. Here is what they did. They created a quantum system, a collection of qubits, the fundamental units of quantum computation, that was designed to simulate the behavior of a simplified model of quantum gravity. This model, developed by Meldesena and others, is called the SYK model, after Suchdev, Yi, and Kitaev, the physicists who originally proposed it. The SYK model is a toy model, a simplified version of a full quantum gravity theory, but it captures some essential features. In this model, you can create a configuration that behaves like a traversable wormhole. Information can go in one side and come out the other, teleported in a way that is consistent with the physics of a wormhole, not just ordinary quantum teleportation. And that is exactly what the team observed. They injected information, encoded in a qubit, into one side of the quantum system, and it emerged from the other side. The signal was transmitted in a way that was consistent with the dynamics of a wormhole, distinct from simple teleportation. The team was careful to point out that this was a quantum simulation, not an actual wormhole in physical space. No spacetime was literally folded. No tunnel through the cosmos was created. But they argued that the simulation captured the essential physics of what a traversable wormhole would do, and that the result was therefore not just a computational trick but a genuine insight into the physics of quantum gravity. Not everyone agreed. Some prominent physicists, including Scott Aaronson, pointed out that the system used in the experiment was far too small and too simple to be meaningfully described as a quantum gravity simulation, and that the word wormhole in the context of this experiment was doing a lot of heavy lifting. The debate continues. But the experiment happened. It was published in Nature, and it represents the closest anyone has come to experimentally probing wormhole physics. And perhaps more importantly, it reflects the degree to which the concept of the wormhole has moved from the fringes to the center of fundamental physics research. Now, here is something that almost nobody talks about when discussing wormholes, and it is one of the most haunting aspects of the whole subject. Even if wormholes exist, even if they form naturally, somewhere in the universe, the conditions inside them may be incompatible with the survival of anything we would recognize as life. This is not just a matter of engineering. It is a matter of fundamental physics. Consider the problem of Hawking radiation. In 1974, Stephen Hawking made one of the most important and disturbing predictions in the history of physics. He showed, using a combination of quantum mechanics and general relativity, that black holes are not entirely black. They radiate. Due to quantum effects near the event horizon, the point of no return around a black hole, pairs of virtual particles are constantly created. Normally, virtual particles appear and annihilate each other immediately. But near the event horizon, it can happen that one particle of the pair falls into the black hole while the other escapes. The escaping particle carries energy, and that energy must come from somewhere. It comes from the black hole itself. The black hole loses mass. Over time, a black hole will radiate away all of its energy and eventually evaporate. This is Hawking radiation. Now, this is deeply relevant to wormholes because if wormholes are related to black holes, if the interior of a wormhole has a structure similar to the interior of a black hole, then Hawking-like radiation processes may occur inside the wormhole. And some calculations suggest that these processes would fill the interior of the wormhole with high-energy radiation. Radiation so intense that it would be lethal to any biological organism, and potentially destructive to any technology sophisticated enough to enter. In other words, even if you could hold the wormhole open with exotic matter, even if you could navigate to the mouth and enter it, the radiation environment inside might kill you before you could traverse it. This is not a certain prediction. The full quantum gravity treatment of the interior of a wormhole is beyond our current theoretical tools, but it is a real concern, and it is one of the reasons that even optimistic physicists are cautious about describing wormholes as potential transportation technology. But let us think bigger. Let us think about what kind of civilization could actually use a wormhole. Physicists and futurists have sometimes used the framework of the Kardashev scale, proposed in 1964 by the Soviet astrophysicist Nikolai Kardashev, to classify civilizations by their energy use. A Type 1 civilization uses all the energy available on its home planet. A Type 2 civilization uses all the energy of its parent star. A Type 3 civilization uses all the energy of its entire galaxy. Human civilization today is somewhere between Type 0 and Type 1. We use only a fraction of the energy available on Earth. By comparison, the task of manipulating exotic matter in quantities sufficient to hold open a traversable wormhole would likely require a Type 2 or Type 3 civilization. We are talking about energy scales that are almost incomprehensibly beyond our current capabilities. But here is the thing. On cosmic timescales, the gap between Type 0 point something and Type 3 is not that large. The universe is 13.8 billion years old. Our species has been using technology for maybe 10,000 years. If we manage not to destroy ourselves in the meantime, a big if, but not an impossible one. And if we continue to develop at even a fraction of our current pace, the capabilities available to humanity in a million years are utterly beyond our current imagination. A million years is a long time in human terms, but barely a heartbeat in cosmic terms. And a civilization a million years ahead of us would not find the problem of exotic matter production to be exotic at all. It might be routine. And if that is true, if advanced civilizations are capable of building traversable wormholes, then the implications for the Fermi paradox are profound. The Fermi paradox is the puzzle name for the physicist Enrico Fermi, who in 1950 reportedly asked, over lunch with colleagues, if there are so many stars in the galaxy, and if many of them have planets, and if some of those planets have life, and if some of that life has become intelligent, and if some of those intelligent civilizations have become technologically advanced, where are they? Where is everybody? The universe is vast and ancient enough that a civilization just a few million years ahead of us could have had time to colonize the entire galaxy many times over. So why don't we see evidence of them? One proposed solution to the Fermi paradox is that advanced civilizations do not colonize space by sending physical ships between stars, a process that is slow, expensive, and limited by the speed of light. Instead, they build wormholes. They establish a galactic network of traversable wormholes, connecting different star systems across the galaxy, and travel between them at will. In this scenario, advanced civilizations might be all around us, thriving and expanding, but invisible to our primitive telescopes because they have outgrown the need to broadcast radio signals. Just as we, today, generate less and less radio frequency leakage as our technology improves. They have graduated to a kind of transit that leaves no trace we know how to detect. This is speculation. It is clearly labeled as such. But it is not frivolous speculation. It follows directly from the physics, and it has been proposed seriously by physicists and SETI researchers as a possible resolution to one of the deepest puzzles in science. And it forces us to ask, in all seriousness, could there be a wormhole network in our galaxy right now, and we simply do not have the instruments to see it? The question of how we would detect a natural wormhole, if one existed, is one that has received growing attention in the past decade. In 2018, Mikhail Popov and colleagues proposed that wormholes might be distinguishable from black holes by the gravitational wave signals they produce during mergers or close encounters. The Event Horizon Telescope, which produced the first black hole images, might in principle be able to distinguish certain types of wormholes from black holes based on the detailed structure of the shadow, the dark region at the center of the image. In 2021, a paper by Rajabul Sheikh and colleagues in Physical Review D argued that certain wormhole metrics produce shadows that are qualitatively different from Schwarzschild black holes and might be detectable with sufficiently precise imaging. In 2023, a preprint by a group of researchers suggested that if a wormhole existed at the center of our galaxy, connecting our universe to another, the gravitational wave signals detectable by LIGO and future observatories like LISA might show distinctive signatures. None of these proposed detection methods have yet found a wormhole. But the fact that we are now at the stage of designing detection strategies, of actually trying to look for them, is itself extraordinary. The wormhole has moved from metaphysics to observational program. We are now, in a real sense, hunting for them. Let us talk about the laws that govern the interior of a wormhole, because they are genuinely bizarre and worth exploring in detail. When you enter a wormhole, you are entering a region of space-time where the curvature is extreme, where the geometry of space and the flow of time are radically different from anything in ordinary experience. But it is important to understand that inside a traversable wormhole, unlike inside a black hole, you are not necessarily trapped. You are not crossing an event horizon. The geometry is different. In a black hole, once you cross the event horizon, all paths in space-time lead toward the singularity. You cannot stop, you cannot reverse direction, you cannot escape. Time itself, in some sense, flows toward the singularity, and you are carried along with it regardless of what you do. A traversable wormhole is not like this. The geometry is set up so that paths through the wormhole lead from one mouth to the other. There is no singularity, no one-way barrier, no event horizon. In principle, you could enter the wormhole, travel part way through, and turn around and come back. You could traverse it in both directions. You could use it as a regular transit corridor, back and forth, as often as you liked. Now, the experience of traversing the wormhole, assuming it were large enough and the tidal forces were manageable, would be unlike any other journey. The geometry of space-time around you would be changing rapidly. The distances between points would be doing strange things. If you looked around as you traveled through the throat of the wormhole, the visual appearance would be highly distorted. Light from outside, from both mouths, would be visible simultaneously, warped and stretched by the extreme curvature. It might look, in some descriptions, like flying through a tunnel with two different skies at each end, both visible at once, the images fish-eyed and distorted but recognizable. And then, if the wormhole connected our solar system to some distant point, you would emerge. The sky would change. The stars would be in different positions. The constellations you had known all your life would be gone, replaced by a new arrangement of light from a new vantage point in the universe. And you would be somewhere, or somewhen, entirely different. Ask yourself this: if you could choose any destination for a wormhole, any place in space, any point in time, where would you go? Would you travel to the future to see what humanity becomes? Would you travel to the past to witness history? Would you cross the galaxy to find other civilizations? Would you cross to another universe to see if other versions of reality exist? This is not idle daydreaming. These are exactly the questions that motivate the physicists who study wormholes. Because the physics does not impose an obvious limit on the destination. The mathematics allows connections to anywhere in spacetime. The only constraints are engineering ones: the amount of exotic matter required, the stability of the throat, the technical challenge of creating and controlling such extreme spacetime curvature. But the physics itself. The physics opens a door that has no obvious lock. And behind that door lies the entire history of time and the entire extent of space. Now let us turn to one of the most disturbing and underappreciated aspects of wormhole physics: the information paradox. The black hole information paradox is one of the deepest and most contentious problems in all of theoretical physics, and it is intimately connected with wormholes. Here is the problem. Quantum mechanics has a principle at its heart called unitarity, which states that information is never destroyed. Every physical process is reversible, at least in principle. If you know the exact quantum state of a system at one moment, you can, in principle, reconstruct the exact state at any other moment. Information is preserved. But Stephen Hawking showed in 1974 that black holes evaporate through Hawking radiation. And when a black hole evaporates completely, what happens to the information that fell in? The matter that formed the black hole, the objects that fell into it over its lifetime, all of that encoded information. Where does it go? Hawking originally argued that it is simply destroyed, that the information disappears when the black hole evaporates, leaving behind only the thermal radiation, which carries no information. But this would be a catastrophic violation of quantum mechanics. It would mean that the fundamental principles of quantum theory do not apply to black holes, that there is a regime of physics where unitarity simply fails. Most physicists find this unacceptable, and for decades, the debate raged without resolution. Then, in 2019, a group of physicists including Ahmed Almhiri, Netta Engelhardt, Donald Merolf, Henry Maxfield, and others made a series of breakthroughs. Using the ADS-CFT correspondence, the same holographic principle that Meldesena discovered in 1997, they showed that information does escape from black holes, carried out by the Hawking radiation in a subtle, quantum-scrambled form. The information is not destroyed. It is encoded in the correlations between the radiation emitted at different times. And crucially, their calculations involved a geometric structure inside the black hole called an island, a region of spacetime that, in the mathematical framework, behaves as though it is part of the exterior of the black hole rather than the interior. And the mechanism that connects the island to the exterior region of the black hole is a wormhole. Specifically, a microscopic wormhole related to the ER=EPR connection discovered by Meldesena and Susskind that connects the interior of the black hole to the radiation field outside. The information escapes through the wormhole. This is extraordinary. It means that wormholes, even microscopic, non-traversable wormholes at the quantum level, may be the mechanism by which the universe preserves the quantum mechanical principle of unitarity. Without wormholes, information would be destroyed in black holes, and quantum mechanics would be fundamentally broken. With wormholes, information is preserved, and the universe remains consistent. Wormholes may not just be transportation shortcuts. They may be a necessary feature of the fabric of reality itself. Let us explore the geography of a wormhole, really walk through it conceptually, because this will help us appreciate what we have been talking about in a much more visceral way. Imagine you are approaching the mouth of a traversable wormhole from outside. From a distance, it looks like a sphere of distorted space-time, like a bubble of warped reality hanging in the vacuum. As you get closer, you begin to see through the sphere. The light bending around and through it creates concentric rings and distortions, like looking through a very thick, perfectly transparent lens. At the center of the sphere, you can see the space on the other side, a window into a different part of the universe, or a different universe entirely, or a different time. The colors might be slightly shifted, blue shifted or red shifted depending on the gravitational potential, but the view is clear, real, unmistakable. You maneuver your spacecraft toward the throat, the entrance. The sphere grows as you approach. At the moment you cross the threshold, the mouth of the wormhole, something subtle happens. The geometry of space-time changes around you. From outside, an observer watching you would see you slow down as you approach the mouth, because the space-time curvature there causes time dilation. But from inside, you feel nothing unusual. You cross the threshold smoothly, without jolt or shock. Inside the throat, the universe looks different. In front of you is the exit, the other mouth, and its light is bending toward you through the curved geometry of the tunnel. Behind you, the entrance is receding. The throat is the narrowest part, the minimum radius of the wormhole, and this is where the exotic matter must be concentrated. The geometry is like the inside of a curved tube, but the curvature is four-dimensional, impossible to fully visualize. The journey through the throat might take moments, or it might take days, depending on the length of the wormhole, which in general relativity can be quite different from the distance between the two mouths in the exterior spacetime. A wormhole connecting 2 points a billion light-years apart might have an interior length of only a few kilometers. The exterior distance and the interior distance are completely independent quantities. They are determined by different aspects of the geometry. And then you emerge. You cross the second threshold. The sphere of the exit mouth expands around you and then falls away behind as you travel outward. The stars are different. The sky is different. You have arrived somewhere new. Now, one of the most remarkable things about traversable wormhole physics is how it forces us to re-examine our most basic intuitions about causality. Causality is the principle that causes precede their effects, that things happen in a certain order, and that order cannot be reversed. You drop a glass, and it falls. The falling comes after the dropping. You cannot have the falling before the dropping. This seems obvious, self-evident, beyond question. But wormholes, especially when combined with the time dilation effects we discussed earlier, allow for what are called closed time-like curves, paths through space-time that loop back on themselves in time. On a closed time-like curve, an object or signal could travel through space-time and arrive at its own past. Cause and effect could become scrambled. The notion of before and after could lose its meaning. And this is deeply troubling to physicists, not just for philosophical reasons, but for physical ones. The existence of closed time-like curves would allow paradoxes, situations where the logic of causality breaks down. The most famous is the grandfather paradox. If you travel back in time and prevent your grandfather from meeting your grandmother, then you would never be born, and therefore you could not travel back in time to prevent the meeting, and therefore the meeting would happen, and therefore you would be born, and therefore you could travel back in time, and so on in an infinite loop. This logical contradiction is, at minimum, deeply uncomfortable. Some physicists respond to it with consistency conditions. They argue that only self-consistent solutions are physically realized, so that anything you do in the past was already part of the history that led to the present. You cannot change the past. You can only be part of it in a way that is consistent with everything that happened. This is sometimes called the Novikov self-consistency principle, proposed by the Russian astrophysicist Igor Novikov. Others, following Hawking, argue that the chronology protection conjecture prevents closed time-like curves from ever forming. And others, more radically, suggest that time travel creates new branches of the wave function, new parallel universes, so that paradoxes are avoided because the time traveler ends up in a branch where their action is consistent. This is the many worlds interpretation of quantum mechanics applied to the time travel problem. All of these responses are interesting. None of them is definitely correct, and the fact that we cannot yet decide between them tells us something important. We are still missing a fundamental piece of the physics. We do not yet have a complete theory of quantum gravity, and until we do, the questions raised by wormholes and time travel will remain open. The pursuit of a theory of quantum gravity, a theory that successfully unifies quantum mechanics and general relativity, is arguably the greatest unsolved problem in theoretical physics. And wormholes sit at the very heart of it. General relativity describes the large-scale structure of space-time with extraordinary precision. It has passed every experimental test ever devised. Quantum mechanics describes the small-scale behavior of matter and energy with extraordinary precision. It is the most accurately tested theory in the history of science. But the two theories are incompatible. They use different mathematical frameworks, they make different assumptions, and when you try to apply both simultaneously, as you must when describing phenomena like the interior of a black hole or the very early universe, they give contradictory results. String theory and loop quantum gravity are the two leading candidate theories of quantum gravity, and both have things to say about wormholes. In string theory, which describes the fundamental entities of nature as one-dimensional vibrating strings rather than point particles, and which requires 10 or 11 space-time dimensions, wormholes arise naturally in many contexts. The higher dimensional geometry of string theory provides ample room for the exotic topology required by wormholes, and many string theorists believe that wormholes will play a central role in the complete theory. In loop quantum gravity, which takes a very different approach, describing space-time itself as a discrete, granular structure at the Planck scale, the smallest physically meaningful length, wormholes also appear in the form of links in the spin network that describes the geometry of space. Both approaches are incomplete. Both have had significant successes and significant failures. And both point toward a reality in which the smooth, continuous spacetime of classical general relativity is just an approximation, an emergent structure that arises from something deeper, something more fundamentally quantum mechanical. And in that deeper structure, wormholes are not exceptional, exotic, or rare. They are woven into the fabric. Let us talk now about one of the most emotionally and philosophically powerful implications of wormhole physics: the possibility that the universe is connected in ways we cannot perceive. Think about what it would mean if wormholes are common, if they exist throughout the universe, connecting distant regions of spacetime, creating a vast network of shortcuts through the cosmos. The universe we observe, the universe we navigate with our instruments and our mathematics, would be just the surface of something far more complex. The apparent distance between galaxies, the billions of light years of void that separate them, would be, in some sense, illusory. Underneath the surface of spacetime, hidden in the quantum foam at the Planck scale, there might be connections everywhere. Every point in the universe might be connected by some microscopic wormhole to every other point. Space might be, at its foundation, not a vast and largely empty expanse, but an intricate, dense, infinitely connected web of quantum tunnels. This vision of a universe that is radically more connected than it appears has a kind of haunting beauty. It transforms loneliness into an illusion. The vast isolation of deep space, the terrifying emptiness between stars and galaxies, is revealed to be a superficial feature of reality, a surface appearance that conceals a deep and intricate connectivity. And when you combine this with the idea that entangled particles are connected by wormholes, that every entangled pair in the universe is linked by a microscopic geometric bridge, you begin to see a cosmos in which connection, relationship, and correlation are not exceptional but fundamental. Not just features of the universe, but the very substance of it. The universe might be not a collection of isolated objects separated by vast distances, but a single, unified, massively interconnected quantum system in which wormholes are the threads that hold it together. This is not yet physics. It is on the border between physics and philosophy. But it is where the physics is pointing. Consider for a moment the specific number involved in wormhole physics that most people never hear. The Planck length, the fundamental minimum length scale implied by quantum gravity, is approximately 1.6 times 10 to the power of negative 35 meters. That is 0.0000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000 The atom is enormous compared to the Planck length. The proton is enormous compared to the Planck length. Even the electron, which as far as we know is a point particle with no spatial extent, would be enormous compared to the Planck length. And yet theoretical physicists believe that at this scale, at distances a trillion times smaller than a proton, the fabric of space-time is not smooth and continuous but boiling with fluctuations. Tiny wormholes bubble in and out of existence at the Planck scale, forming and collapsing in times of order 10 to the minus 44 seconds, the Planck time. This quantum foam is not directly observable by any technology we can currently imagine, but it is predicted by the equations. And it means that wormholes, at the most microscopic level, are not rare or hypothetical. They are everywhere, constantly, at the foundation of reality itself. The universe is made of wormholes. We just cannot see them yet. Now ask yourself another question. What does it mean for your understanding of the universe to learn that the very space you occupy, the apparently empty room around you right now, the air in front of your face, is, at its most fundamental level, a seething, churning foam of microscopic wormholes, constantly appearing and disappearing, connecting and disconnecting, weaving and unweaving the fabric of reality? How does that change the feeling of the space around you? Does it feel emptier or fuller? Stranger or more familiar? More connected or more alien? These questions are worth sitting with, because the answers say something about what it means to be a conscious being embedded in a quantum mechanical universe. Let us turn now to one of the most science fiction sounding but physically legitimate proposals in the wormhole literature. The idea of using a wormhole not for transportation but for communication. Even if the amount of exotic matter required to hold open a traversable wormhole large enough for a human body is impossibly large. At least for now, the amount required to hold open a wormhole large enough for a single photon of light might be much smaller. A microscopic wormhole, too small for anything material to pass through, but large enough for a signal, could in principle serve as a faster-than-light communication channel. Or more precisely, as a communication channel that connects two distant points in spacetime without the signal having to traverse the intervening space. This is distinct from faster-than-light travel in an important sense. Information could in principle be transmitted through such a channel without any object physically moving faster than light. The signal would travel through the wormhole rather than through the conventional spacetime between the 2 points. Now, there is an important caveat here. The no-communication theorem of quantum mechanics states that quantum entanglement alone cannot be used to transmit information faster than light. But this theorem applies to the standard quantum mechanical framework. Whether it applies in full when quantum gravity effects are included, when microscopic wormholes of the ER equals EPR type are taken into account, is precisely what is being debated in the current literature. Some physicists argue that the 2022 quantum computer experiment by Spiropoulou and colleagues is directly relevant here, that the mechanism they demonstrated, which involves what they call quantum teleportation through the wormhole, is a form of information transfer that is distinct from ordinary teleportation and that provides a new way of thinking about how information propagates through spacetime. Again, the debate is ongoing. The experiment is real. The interpretation is contested. But the direction is thrilling. There is another aspect of wormhole physics that deserves careful attention, and it is one that most popularizations of the topic completely miss. The question of stability. Even if you could create a traversable wormhole, even if you had enough exotic matter to hold it open, the wormhole might be dynamically unstable. This means that small perturbations, tiny fluctuations in the geometry or the matter distribution, might cause the throat to either collapse or inflate catastrophically, rather than remaining at a stable size. Think of it like balancing a ball on top of a hill. In principle, the ball can sit at the top, perfectly balanced. But in practice, the slightest nudge sends it rolling down. A wormhole that is only marginally stable, that sits at a mathematical balance point between collapse and explosion, would be extraordinarily difficult to maintain. You would need to actively control the geometry, adding or removing exotic matter in response to fluctuations, in a kind of dynamic balancing act. Whether the physics allows stable equilibria for wormholes, genuinely stable configurations rather than balance points, is a question that depends on the details of the exotic matter and the wormhole geometry. Some theoretical models suggest that stable configurations do exist. Others suggest that all traversable wormholes are unstable on some timescale. The resolution of this question likely requires a complete theory of quantum gravity, which we do not yet have. Now, let us talk about something that is rarely discussed in the context of wormholes, but that is actually deeply important for understanding what they mean: the arrow of time. We are all familiar with the experience of time moving in one direction, from past to future. Eggs break, they do not spontaneously reassemble. Smoke disperses, it does not reconcentrate. Memories of the past exist, memories of the future do not. The second law of thermodynamics, which states that entropy, the measure of disorder in a system, always increases in a closed system over time, is one of the most fundamental and empirically robust laws in all of physics. The arrow of time is real, and it points resolutely forward. But the underlying laws of physics, quantum mechanics, and general relativity are time-symmetric. They work exactly the same way running forward or backward. There is nothing in the fundamental equations that picks out a preferred direction of time. The arrow of time emerges from the initial conditions of the universe. The universe began in an extraordinarily low entropy state at the Big Bang, and entropy has been increasing ever since, giving us the arrow of time we experience. Wormholes challenge the arrow of time in a very deep way. If a wormhole can connect two different times, if you can enter one mouth in the present and exit the other mouth in the past, then the apparently unidirectional flow of time is revealed as a local, not global, feature. In the geometry of space-time, past and future are just different directions in four-dimensional space. Time is not fundamentally different from space. It is just another dimension with its own metric, its own geometry, its own curvature. And wormholes, by connecting different time-like directions, are a reminder that the universe does not care about our subjective experience of the flow of time. It cares about the geometry of space-time, and in that geometry, past and future are symmetric, reversible, potentially connected. Let me tell you about one of the most unusual and captivating papers in the history of wormhole physics. In 1994, a physicist named Miguel Alcubierre, working at the University of Wales, published a paper titled The Warp Drive: Hyperfast Travel Within General Relativity, in which he described a hypothetical space-time geometry that would allow a spacecraft to travel to distant stars faster than light without violating any known law of physics. The mechanism: a bubble of warped space-time that contracts the space in front of the ship and expands the space behind it, effectively moving the ship through space without the ship itself moving faster than light relative to any local point. The ship is carried along by the geometry, like a surfer riding a wave. The Alcubierre warp drive is not the same as a wormhole, but it is deeply connected. Both mechanisms exploit the same fundamental insight. In general relativity, the geometry of spacetime is dynamic and controllable, and by manipulating the geometry, you can effectively achieve relative motion that exceeds the speed of light without violating special relativity. And both mechanisms require exotic matter with negative energy density. The Alcubierre warp drive, like the traversable wormhole, requires a quantity of exotic matter that is, under naive calculations, impossibly large, comparable to the mass energy of Jupiter in negative form. However, subsequent work by Harold White at NASA's Johnson Space Center showed that modifications to the geometry of the warp bubble could reduce this requirement dramatically. Whether White's calculations are fully correct is debated, but the direction is encouraging. And the fundamental physics, the mathematical existence of the Alcubierre solution within general relativity, is not in doubt. In other words, In the same mathematical universe that contains wormholes, there are also warp drives. Einstein's equations are extraordinarily permissive. They allow a universe that is, by our current engineering standards, shockingly navigable, if you can master the geometry. Before we reach the final and perhaps most astonishing fact in this exploration, let us pause and take stock. We have established that wormholes are mathematical solutions to Einstein's equations. They are not invented by science fiction writers, but by the equations that describe the geometry of spacetime. We have established that the original Einstein-Rosen bridge is not traversable. It collapses too quickly for anything to pass through. We have established that traversable wormholes are theoretically possible, requiring exotic matter with negative energy density, and that negative energy density is physically real, as demonstrated by the Casimir effect. We have established that traversable wormholes would function as time machines, allowing travel to the past or future, and that this raises deep questions about causality and the arrow of time that are not yet resolved. We have established that wormholes may be connected to quantum entanglement through the ER equals EPR conjecture proposed by Meldesena and Susskind, and that this connection may be fundamental to the structure of spacetime itself. We have established that wormholes may be the mechanism by which information escapes from evaporating black holes, preserving the quantum mechanical principle of unitarity. We have established that quantum foam at the Planck scale consists of microscopic wormholes constantly appearing and disappearing, potentially making wormholes a fundamental, ubiquitous feature of the fabric of reality. We have established that wormholes might connect not just different regions of our universe but different universes entirely. And we have established that physicists are now actively searching for observational signatures of natural wormholes, using gravitational wave detectors and very long baseline interferometry. All of this is physics. All of it is sourced in peer-reviewed literature. All of it is being studied by some of the greatest minds alive today. And now we arrive at the 11th fact, the one that is, in many ways, the most extraordinary of all. In 2019, a group of physicists working on the problem of quantum gravity and the black hole information paradox, including Ahmed Almhairi, then at the Institute for Advanced Study, Jeffrey Pennington at UC Berkeley, Netta Engelhardt at MIT, and others, published a series of papers that collectively represent one of the most significant breakthroughs in theoretical physics in decades. These papers, which built on the work of Meldesena, Susskind, and many others, showed something stunning. They showed that the interior of a black hole, the region inside the event horizon, which was traditionally understood to be causally disconnected from the rest of the universe, isolated forever from any outside observer, is, in the full quantum gravitational treatment, connected to the outside world. Not metaphorically connected, geometrically connected, through a wormhole. The resolution of the black hole information paradox. The answer to where the information goes when a black hole evaporates is that the information does not go anywhere outside the universe. It stays connected to the outside through a network of microscopic wormholes, invisible at the classical level but fundamentally present in the quantum gravitational description. The interior of the black hole, in this picture, is not truly separate from the exterior. The quantum gravitational geometry includes a wormhole connection, related to the ER equals EPR structure, that links the interior to the Hawking radiation and preserves the information. This is not a peripheral result. It is not a minor technical correction. It is a fundamental revision of our understanding of what black holes are and how they work. It means that the classical picture of a black hole, a region of spacetime enclosed by an event horizon, permanently and completely cut off from the rest of the universe, is wrong. Or rather, it is an approximation that breaks down in the quantum gravitational regime. In the full quantum mechanical picture, black holes are not isolated. They are connected, and the connection is through wormholes. In other words, in the universe as quantum gravity describes it, there are no truly isolated regions of spacetime. Everything is connected. The wormhole, the tunnel through spacetime, is not a rare, exotic possibility. It is a fundamental and necessary feature of quantum gravitational physics. The universe is not a collection of isolated regions connected only by the slow, classical flow of light through the void. It is a quantum gravitational web, connected at every scale, from the largest black holes to the smallest Planck scale fluctuations, by the threads of wormholes and entanglement that weave the fabric of space-time together. This is the universe that physics is revealing to us. And it is stranger and more beautiful and more connected than anything we imagined. Now, you might be wondering, you might genuinely be sitting there wondering, whether any of this will ever leave the realm of theory. Whether wormholes will remain forever a piece of beautiful mathematics, elegant and profound, but never touching the physical world in any way you can experience. That is a fair question, and it deserves a serious answer. Here is the serious answer. The history of physics is replete with examples of mathematical predictions that seemed impossible to test or impossible to realize, and that later turned out to be not just testable but transformative. Radio waves were predicted mathematically by James Clerk Maxwell in 1865, before they were ever generated in a laboratory. Nuclear energy was predicted by Einstein's famous equation E=mc² in 1905, long before the first nuclear reactor. Gravitational waves were predicted by Einstein in 1916, and the first direct detection did not come until 2015, 99 years later. In each case, the mathematics was right, the physics was right, and eventually the technology caught up. The detection of gravitational waves by LIGO is, in this context, a very important data point. Because the detector required for that achievement, a laser interferometer sensitive enough to detect a change in length of 1,000th the diameter of a proton over a 4-kilometer baseline, was, in the early 20th century, a fantastical engineering impossibility. Nobody in 1916 could have imagined building such a machine. And yet it was built. And it works. And it has opened an entirely new window on the universe. The technology required to produce exotic matter in controlled quantities, to engineer the space-time geometry of a wormhole, is fantastical by today's standards. But fantastical by the standards of today does not mean impossible by the standards of tomorrow. The arc of physics bends toward understanding, and the history of understanding bends toward capability. The question is not whether wormholes will ever be relevant to engineering. The question is when. And in the meantime, the theoretical understanding of wormholes continues to advance at a pace that is remarkable even by the standards of modern physics. The ER=EPR conjecture continues to generate new insights. The black hole information paradox continues to be refined. The quantum simulation community continues to explore wormhole dynamics on quantum computers. New proposals for detecting astrophysical wormholes continue to appear in the literature. And at the philosophical frontier, physicists are grappling with what the wormhole-centric picture of spacetime means for our deepest questions. What is spacetime made of? Is space a fundamental thing? Or does it emerge from something more primitive? Is time a dimension or an illusion? Are there other universes, and can we reach them? Is the universe fundamentally local? Is every cause connected only to nearby effects? Or is it fundamentally non-local, with distant points connected by the quantum threads of entanglement and wormholes? These questions are no longer just philosophy. They are physics. They are being asked by people with chalk and equations and quantum computers, and the answers are starting to come in. And the answers are saying, the universe is more connected than you thought. The universe is more traversable than you thought. The universe is more strange, more beautiful, more shocking than you thought. And in that strangeness and beauty and shock, there is a kind of hope. The hope that what looks like an impassable void might be, underneath its surface, a door. The hope that the vast and lonely cosmos might be, in its quantum gravitational reality, a web of connections rather than an ocean of isolation. The hope that the future of the human species is not confined to the tiny, fragile pale blue dot we currently inhabit, or even to the small corner of the galaxy we might someday reach with conventional rockets, but extends, through the wormholes in the fabric of reality, to the entire breadth of the universe. And perhaps beyond. Let us go deeper into the theoretical mechanics of the Morse thorn wormhole. the traversable wormhole geometry that Kip Thorne and Michael Morris worked out in 1988 and subsequently refined, because understanding the specific mathematical constraints reveals just how carefully nature has designed these potential structures, and how carefully we would need to design our own. The Morris-Thorne wormhole is characterized by a metric, a mathematical description of the geometry of spacetime that has a specific, carefully chosen form. The key features are these. First, there is no event horizon. In a black hole, the event horizon is the surface of no return, the boundary beyond which nothing, not even light, can escape. The Morris-Thorne wormhole geometry is carefully designed to avoid event horizons, so that passage through the wormhole is possible in both directions. Second, the curvature is finite everywhere. In a black hole, the geometry contains a singularity, a point where the curvature becomes infinite and the equations break down. The Morris-Thorne wormhole has no singularity. The curvature varies, reaching its maximum at the throat, but remains finite throughout. Third, the tidal forces are manageable. Tidal forces are the differences in gravitational pull across the extent of your body, the same forces that would tear you apart near the singularity of a black hole. In the Morris-Thorne wormhole, the geometry can be chosen so that the tidal forces at the throat are small enough for a human being to survive, comparable to, say, the tidal forces near the surface of the Earth. Fourth, and most importantly, the exotic matter required is concentrated at the throat. The negative energy density is not spread throughout space, but is localized at the narrowest part of the wormhole. This is actually helpful from an engineering standpoint, because it means you do not need to fill the entire wormhole with exotic matter. You need to line the throat like the wall of a tunnel. Morris and Thorne showed that by choosing appropriate geometries, you can design traversable wormholes with different properties, large or small, near or far, connecting nearby regions of spacetime or distant ones. The mathematical freedom is enormous. The physics allows great variety. What it does not allow, what it absolutely insists on, is the exotic matter at the throat. That requirement is non-negotiable. The price of a traversable wormhole is negative energy density at the throat, and that price must be paid in full. And here is where we need to talk more carefully about just how strange exotic matter would be, and what its physical consequences would be beyond simply holding the wormhole open. Exotic matter with negative energy density would behave in ways that are radically contrary to all ordinary experience. Normal matter, the stuff you and everything around you is made of, has positive energy density and positive pressure. It gravitates attractively. It pulls other matter toward it. It is pulled toward other matter, and in sufficient quantities it causes spacetime to curve in the way that produces gravity as we know it. Exotic matter with negative energy density would gravitatize repulsively. Instead of pulling, it would push. Instead of creating an attractive gravitational field, it would create a repulsive gravitational field. An object near a lump of exotic matter would be pushed away from it, not drawn toward it. This is sometimes called anti-gravity, though that term is imprecise and loaded with science fiction connotations. The more accurate description is that exotic matter would produce a negative contribution to the stress-energy tensor, the mathematical object in Einstein's equations that represents the source of spacetime curvature, and this negative contribution would curve spacetime in the opposite direction from ordinary matter. In a wormhole, this anti-gravitating property is exactly what you need. The wormhole throat wants to collapse. The geometry tends toward pinching off, just like the original Einstein-Rosen bridge. The exotic matter at the throat pushes back against this tendency, curving spacetime outward instead of inward, keeping the throat open like a structural material in a tunnel. The exotic matter is, in this sense, the load-bearing material of the wormhole, the steel and concrete that prevents the tunnel from collapsing. Except it is not steel and concrete. It is negative energy, stranger than anything in engineering experience, operating at the edge of what physics allows. The cosmological implications of exotic matter are also deeply interesting and potentially observationally relevant. We know from astronomical observations, from the precise measurements of the cosmic microwave background by the Planck satellite, from the observation of distant Type Ia supernovae, and from the large-scale structure of the universe, that the expansion of the universe is accelerating. Galaxies are moving apart from each other at an increasing rate. This acceleration is driven by something called dark energy, a form of energy with negative pressure that fills all of space and causes the expansion to speed up. The nature of dark energy is one of the greatest mysteries in modern cosmology. It comprises approximately 68% of the total energy content of the universe, but its fundamental nature is completely unknown. One of the simplest models of dark energy is the cosmological constant, a fixed energy density of empty space, which Einstein himself introduced into his equations in 1917, before the expansion of the universe was discovered, and later called his greatest blunder. But more complex models of dark energy involve a dynamical field, sometimes called quintessence, that varies in space and time. And some models of dark energy have the same property that exotic matter requires: negative energy density in some sense, or at least a violation of what are called the energy conditions. The energy conditions are a set of inequalities in general relativity that ordinary matter always satisfies, and that are violated by exotic matter. If dark energy violates the energy conditions in the right way, and some models suggest it does, then in a very loose sense, the universe is already filled with exotic matter. Not in concentrated form, not at the throat of a wormhole, but diffusely everywhere, as the dark energy that drives cosmic acceleration. This does not mean that wormholes are easy to make. Even if dark energy violates the energy conditions, the concentration required at a wormhole throat is many, many orders of magnitude beyond the diffuse dark energy density. But it does suggest that exotic matter, negative energy, energy condition violation, is not a foreign intruder in the universe. It may be woven into the cosmic fabric itself. Now, let us take a dramatic step and consider what wormholes mean for the very long-term future of the universe. The universe, according to our best current understanding, is heading toward a fate called the heat death, a state of maximum entropy in which all stars have burned out, all black holes have evaporated, and the universe is a cold, dark, featureless expanse of dilute radiation. This is expected to occur on a timescale of roughly 10 to the 100 years, a googol years, an almost incomprehensibly long time in the future. In a universe without wormholes, the heat death seems inevitable. But in a universe with wormholes, especially if wormholes connect different regions of space-time, the picture might be more complex. Some physicists have speculated that in a universe with traversable wormholes, a sufficiently advanced civilization might be able to manipulate the topology of space-time in ways that alter the thermodynamic fate of the universe. By connecting regions of different entropy through wormholes, you could in principle transfer entropy from one region to another, not decrease total entropy, which the second law prohibits, but distribute it differently. You could, in a very distant theoretical sense, engineer the universe at a cosmological scale to extend the period of low entropy and thus the period in which complex structures, life, intelligence, civilization, can exist. This is extremely speculative. It is not physics in any conventional sense. It is more like science fiction physics or cosmological engineering fiction. But it is logically consistent with the framework of general relativity as we currently understand it. And it illustrates just how transformative the existence of traversable wormholes would be, not just for individual civilizations, but for the universe as a whole. Now, let us address the question that many people find most fascinating and most troubling about wormholes. Would you survive passing through one? We have mentioned tidal forces and radiation, but let us think about this in a more holistic way, considering everything the physics tells us. First, the tidal forces. If the wormhole is large enough, if the throat radius is large compared to the distance over which the curvature changes significantly, then the tidal forces at any given point inside the wormhole will be small. This is the same reason that you do not feel the tidal forces of the Earth's gravity as you stand on its surface. The tidal differential across your body height is tiny compared to the total gravitational acceleration. For a large wormhole, large enough for a ship, the tidal forces could be within survivable limits. Second, the radiation environment. As we discussed, Some calculations suggest that quantum vacuum fluctuations inside a wormhole might produce a radiation field analogous to Hawking radiation near a black hole. The intensity of this radiation would depend on the details of the wormhole geometry and the nature of the exotic matter holding it open. In the worst case, the radiation might be lethal. In the best case, for a large, gently curved wormhole, it might be negligible. We do not yet have the theoretical tools to calculate this precisely. Third, the psychological and physiological effects of passing through a region of extreme space-time curvature. Interestingly, in a sufficiently large wormhole, these might actually be modest. The laws of physics, as they would apply locally to an observer inside the wormhole, are the same laws that apply everywhere. You would not suddenly lose the ability to breathe or think or move. Your biological processes, governed by electromagnetism and quantum mechanics and chemistry, would continue as normal. You would be embedded in a curved spacetime, yes, but a smooth, finite, non-singular curved spacetime. The journey might, in the best case, feel entirely unremarkable from the inside. And then the sky would change, and you would know that you had arrived. The narrative of the wormhole in popular culture is one of the most interesting aspects of how this concept has permeated human imagination. The idea of a shortcut through space has been a staple of science fiction since at least the mid-20th century. Space opera, from Asimov's Foundation series to Ursula K. Le Guin's Hainish cycle to Frank Herbert's Dune to Star Wars, has always required some mechanism for moving characters between star systems faster than the speed of light would allow. For most of these narratives, the mechanism was not carefully specified. Hyperspace, faster-than-light drives, the Holtzman effect of Dune's spice-fueled space-folding navigators. These were storytelling devices, not physics. But as the physics of wormholes became better understood and more widely publicized through the 1980s and 1990s, helped enormously by Carl Sagan's Contact and the popular science writings of Kip Thorne himself, science fiction began to engage with the actual physics more seriously. The most remarkable example is Christopher Nolan's Interstellar, released in 2014, which was produced in close collaboration with Thorne and which made genuine efforts to represent the physics accurately. The spherical wormhole appearance, which we described earlier, the time dilation effects near the massive planet, the visualization of the black hole with its accretion disk, which was so accurate that it led to a scientific publication, because the simulations revealed new astrophysical phenomena that the team had not anticipated. Thorne wrote a companion book to the film, The Science of Interstellar, which remains one of the finest popular explorations of these topics available. And beyond Interstellar, the concept of the wormhole has appeared in serious science fiction with increasing frequency and increasing accuracy. In Ted Chiang's Story of Your Life, in Alastair Reynolds' Revelation Space Universe, in Kim Stanley Robinson's Aurora, and in many others. The culture is learning the physics. Slowly, imperfectly, but genuinely. And that matters because public understanding of physics shapes what gets funded, what gets studied, and what kinds of futures we dare to imagine for ourselves. Let us also discuss a potential natural wormhole candidate that has been proposed in the scientific literature, because this is not as far-fetched as it might sound. In 2014, a pair of physicists, Nikodem Poplawski, working at the University of New Haven, published a paper proposing that every black hole might be the entrance to a wormhole, and that new universes might be born through the singularities of black holes. In Poplawski's model, which uses a variant of general relativity called Einstein-Cartan theory that incorporates a geometric quantity called torsion, the singularity of a black hole is replaced by a bridge, a wormhole that connects the black hole to a new region of spacetime. From the outside, the black hole looks like a normal black hole. But inside, the geometry of spacetime does not terminate at a singularity. Instead, it expands into a new region, a new spacetime that could be an entire universe unto itself. In this model, our own universe might have originated as the interior of a black hole in a parent universe. The Big Bang, the moment of extremely high density and temperature that began our cosmos, might be the image, from inside, of a black hole forming in a parent universe. And every black hole in our universe might be spawning a new child universe, nested inside. This is a wild idea. It is controversial. It is not mainstream physics. But it is published in peer-reviewed journals. It is based on a mathematically consistent extension of general relativity, and it is taken seriously by a subset of physicists who work on quantum gravity and cosmology. And it connects to an idea proposed earlier by the physicist Lee Smolin, who called it cosmological natural selection. The idea that universes reproduce through black holes, and that the physical constants of daughter universes are slightly different from those of the parent. If universes with more black holes produce more offspring, and if the physical constants that promote black hole formation are heritable in some sense, then over many generations of universe reproduction, the physical constants would evolve, by a process analogous to natural selection, toward values that maximize black hole production. Remarkably, this leads to predictions. Smolin's model predicts that the physical constants of our universe should be close to optimal for black hole production. Whether this is actually true is debatable, but the idea is testable in principle, which makes it science rather than philosophy. Now, let us take a moment to discuss the people who are doing this work today. The living, breathing physicists who spend their days and nights thinking about wormholes. Because the wormhole is not a historical curiosity. It is an active area of research at some of the most prestigious institutions in the world. Juan Meldacena at the Institute for Advanced Study in Princeton, the same building where Einstein worked, continues to develop the ER=EPR framework and its implications for quantum gravity. Netta Engelhardt at MIT, who shared a New Horizons in Physics Prize in 2021 for her work on the information paradox and quantum extremal surfaces, the geometric objects related to wormholes that resolve the paradox. Jeffrey Pennington at UC Berkeley, who independently and simultaneously discovered the island formula for black hole entropy, the key result that wormholes preserve information. Maria Spiropoulou at Caltech, who led the quantum computer wormhole simulation. And at institutions around the world, in Europe, in Asia, in North America, in South America, there are hundreds of physicists working on aspects of wormhole physics, quantum gravity, the information paradox, the AD-SCFT correspondence, and the ER=EPR conjecture. This is not a small or marginalized field. It is one of the most active and well-funded frontiers in theoretical physics. The world's best young physicists are choosing to work on these problems. The world's most prestigious prizes are being given to people who have made progress on these problems. The attention of the physics community is, more than at any previous moment in history, focused on the questions that wormholes raise. We are living through a golden age of theoretical physics, driven in large part by the puzzle of what wormholes mean and how quantum gravity works. And the gold being mined from this age will, in the fullness of time, transform our understanding of reality itself. Let us talk about one more extraordinary theoretical development: the concept of designer wormholes. This sounds like science fiction, but it is the subject of a growing body of theoretical literature. The idea is this: given the freedom that Einstein's equations allow in specifying the geometry of spacetime, given that you can in principle choose the metric of a traversable wormhole quite freely, subject only to the requirement of exotic matter, physicists have asked, what would an optimal wormhole look like? A wormhole optimized for transit time, for safety, for stability, for minimum exotic matter, for specific causal properties. And the results of these optimization studies are fascinating. For instance, papers by Francisco Lobo and others have explored wormhole geometries that minimize the amount of exotic matter required, finding configurations that need much less exotic matter than the naive estimates suggest. Papers by Pedro Gonzalez, Yerlim Merzakulov, and colleagues have explored wormholes in modified theories of gravity, theories that deviate from Einstein's general relativity in specific, controlled ways, and found that in some of these theories, traversable wormholes can exist with ordinary matter, without any exotic matter at all. These modified gravity theories are not speculative in the pejorative sense. Many of them are motivated by the desire to explain dark energy or dark matter, and they are taken seriously by large communities of physicists. If any of these modified gravity theories is correct, then the exotic matter barrier to traversable wormholes might not exist. Wormholes might be accessible with matter of the type that already exists in the universe, without any need for engineering negative energy densities. And in that case, nature itself might have already created them. One of the questions that often comes up in discussions of wormholes is, how long would it take to traverse one? And the answer is both counterintuitive and fascinating. The interior length of a wormhole, the distance you would travel through the wormhole from mouth to mouth, is independent of the exterior distance between the mouths. A wormhole connecting 2 points a billion light-years apart might have an interior length of just a few meters, or a few kilometers, or a few hundred kilometers. From the outside, the 2 points are separated by a billion light-years of space. From the inside, the journey might take minutes. This is the essence of the wormhole as a shortcut. Not that you travel faster than light in any local sense, but that you travel a much shorter actual distance. You do not violate the cosmic speed limit. You take a different road. The analogy with the folded piece of paper is perfect here. The worm does not move faster across the apple's surface. It bores through the apple. And the distance through the apple is far less than the distance around the surface. Now, within the wormhole, you are still limited to traveling at the speed of light or below. You still experience time passing. You still obey all the local laws of physics. But because the distance is so short, the time required to traverse it is correspondingly short. A billion light-year journey reduced to a kilometer-length interior might take, even at a modest velocity, only a few seconds. In principle, you could step through a wormhole and emerge a billion light-years away, having experienced only seconds of travel time. The universe, which looked unimaginably vast, would be suddenly, astonishingly, intimate. And now let us talk about what that means emotionally. Because the emotional impact of the wormhole concept is not just intellectual curiosity, it is something deeper. Human beings experience the vastness of the universe as a kind of existential loneliness. We look up at the night sky and feel small, isolated, adrift in an incomprehensibly large cosmos that is utterly indifferent to our existence. The nearest star system, Alpha Centauri, is 4.2 light-years away. At the highest speed ever achieved by a human spacecraft, the Parker Solar Probe, which reached about 160 kilometers per second in 2023, it would take approximately 7,900 years to reach Alpha Centauri. 7,900 years. The entire recorded history of human civilization is only about 5,000 years. The nearest star is so far away that we could not reach it even by sending a spacecraft at the speed of our fastest probe and waiting longer than civilization has existed. This is the existential situation of the human species. We are embedded in a universe that is beautiful and astonishing, but we are also essentially trapped, confined by the speed of light to a tiny bubble of accessible space around our home star. The wormhole changes this. Not today, not this century, perhaps not this millennium. But in principle, if wormholes are real and if they can be made traversable, the human species would not be trapped. The universe would not be an exile from which there is no escape. It would be a landscape to explore, a network to traverse, a home without walls. And that possibility, even as a theoretical, distant, uncertain possibility, transforms the emotional weight of the cosmos. It transforms the night sky from a symbol of our smallness into an invitation. It transforms the silence of deep space from a void of isolation into a waiting threshold. It says, in the language of mathematics and physics, the universe is not as large as it seems. It is folded, and in the folds, there are doors. There is something else that deserves to be said about wormholes and the nature of scientific discovery. The history of science is a history of unexpected connections, of seemingly separate things turning out to be the same thing in disguise. Electricity and magnetism turned out to be two aspects of the same force, electromagnetism. Space and time turned out to be two aspects of the same fabric, space-time. Matter and energy turned out to be interconvertible, E=mc². Particles and waves turned out to be two descriptions of the same quantum object. And now, In the early 21st century, we are witnessing what appears to be another extraordinary convergence. Wormholes and quantum entanglement appear to be two descriptions of the same geometric structure. Gravity and quantum information appear to be two aspects of the same underlying reality. Space-time and quantum circuits appear to be related by a deep duality. The biggest ideas in physics are once again converging, and the wormhole sits at the intersection. This is not accidental. It is a sign that physics is approaching something fundamental. Some deeper layer of reality that unifies all the disparate pieces. And when we find it, when the theory of quantum gravity is finally written down, the wormhole will not be an exotic solution in the appendix. It will be a central feature of the landscape. The hole in the fabric will turn out to be a thread in the weaving. Ask yourself this: what does it feel like to live in a universe that contains wormholes? Not a universe where wormholes are hypothetical, a universe where they are real, physical structures embedded in the geometry of space-time, connecting distant points, potentially housing information, potentially spawning new universes from the depths of black holes, potentially weaving the fabric of space-time itself from the threads of quantum entanglement. What kind of universe is that? It is a universe that is, at its deepest level, profoundly relational. A universe in which isolation is an illusion and connection is fundamental. A universe in which the apparent emptiness of space conceals an underlying fullness. A richness of geometric connection that our ordinary senses cannot perceive but that our mathematics has begun to uncover. It is a universe that rewards curiosity. A universe that opens up the further you look. A universe that is, in the truest sense, stranger and more wonderful than we could have imagined. And it is the universe we live in. Not a fictional universe. Not a thought experiment. The universe. This one. The one in which you are breathing and thinking and reading right now. The one whose stars you see on clear nights and whose quantum vacuum surrounds you on all sides in every moment. The one whose geometry, at the Planck scale, is frothing with microscopic wormholes, constantly appearing and disappearing, weaving the fabric of space-time from the bottom up. You live in a universe full of wormholes. And that is one of the most extraordinary facts in the history of thought. Now, let us consider the experimental roadmap going forward. Because if the theoretical picture we have described is correct, or even partially correct, what are the concrete steps that physics must take in the coming decades to confirm it, refine it, and eventually exploit it? The first priority is the continued development of the Event Horizon Telescope and its successors. The Event Horizon Telescope, the global network of radio telescopes that produced the first black hole images, is already being upgraded. The next generation Event Horizon Telescope, currently in planning, will have higher resolution, more telescope stations, and better sensitivity. It will be able to image the shadow of Sagittarius A star with much greater detail, and it may be able to detect subtle differences between a Schwarzschild black hole and a Kerr black hole, or between a black hole and a wormhole, if any natural wormholes are present in the galactic center. The second priority is the development of next-generation gravitational wave detectors. The current LIGO detectors are extraordinary machines. They detect space-time distortions 1,000 times smaller than the diameter of a proton, but they are limited in their frequency range and sensitivity. The planned Einstein telescope in Europe and Cosmic Explorer in the United States will be far more sensitive. And the planned LISA mission, the Laser Interferometer Space Antenna, will operate in space, sensitive to much lower frequency gravitational waves, and potentially able to detect the gravitational wave signatures of wormhole-like structures. The third priority is the continued development of quantum computers capable of simulating quantum gravity. The 2022 experiment by Spiropoulou and colleagues used 9 qubits on a machine with 53 qubits in total. Future quantum computers with hundreds or thousands of qubits will be able to simulate much larger and more realistic quantum gravity systems, potentially providing detailed information about the dynamics of wormholes in the ER=EPR framework. The fourth priority is experimental exploration of the Casimir effect and related quantum vacuum phenomena, with the goal of understanding the limits of negative energy production and whether those limits can be pushed in ways relevant to wormhole physics. The fifth and most speculative priority is the development of entirely new experimental techniques, ways of probing the Planck scale, the quantum foam, the microphysics of wormholes that we have not yet imagined. Just as gravitational wave detection required an experimental technique that nobody in 1916 could have conceived, the detection and study of wormholes may require a technique that nobody today can conceive. History suggests we should expect this and hope for it. Before we come to our conclusion, let us revisit the human dimension of this story one more time, because it is easy, in the excitement of the physics, to forget that all of this knowledge has been built by human beings. By people who got up in the morning and went to work in offices and blackboards, who ate lunch with colleagues, who had arguments and made mistakes and revised their conclusions and sometimes had moments of breakthrough that left them shaking with excitement. Karl Schwarzschild, who derived the first solution to Einstein's equations while shells were falling on the Russian front in World War I, and who died of a disease contracted at the front less than a year later, never knowing what his equations implied about the wormhole. Albert Einstein, who spent the last 30 years of his life trying to develop a unified field theory that would subsume quantum mechanics into a classical geometrical framework, and who failed, but who left behind, in the 1935 Einstein-Rosen paper, the seed of one of the most fertile ideas in the history of physics. John Archibald Wheeler, who coined the name wormhole and who spent decades advocating for the view that quantum mechanics and general relativity must be unified, who saw in the quantum foam of spacetime not chaos but a kind of deep order. Kip Thorne, who spent his career developing the physics of extreme spacetime curvature, who collaborated with Carl Sagan to make the science of wormholes accessible to the public, who helped produce Interstellar, and who in 2017 accepted the Nobel Prize on behalf of himself and his colleagues for the detection of gravitational waves, an achievement that demonstrated the reality of the spacetime geometry that makes wormholes possible. Stephen Hawking, who argued that wormholes cannot be used for time travel and who spent his entire career working at the intersection of quantum mechanics and general relativity, often from a wheelchair, often in chronic pain, never stopping. Juan Meldacena, who grew up in Argentina and who, in 1997, published a paper that connected gravity and quantum mechanics in a way that is still transforming physics a quarter-century later. Netta Engelhardt, who in her mid-30s has already made contributions to the information paradox that her field considers epochal. These are human beings. Curious, persistent, fallible, brilliant human beings who have spent their lives trying to understand the universe that contains us. And what they have found, what they are finding right now, in laboratories and offices and lecture halls around the world, is that the universe is more extraordinary than any of them expected, and that the wormhole, the hole in the fabric of spacetime that Einstein and Rosen sketched out in 1935, is not a curiosity or a footnote. It is a key, and we are still learning what locks it opens. There is one final aspect of the wormhole story that we have not yet fully explored, and it is perhaps the one most laden with both wonder and dread. It is the question of what lies at the other end. Not in the technical sense, not the question of which region of spacetime the other mouth opens into, which can in principle be specified by the geometry, but in the deeper sense. If wormholes are real and traversable, and if an explorer entered one and traveled through to the other side, what would they find? What is out there, in the vast, unexplored reaches of the universe that we have never visited and may never visit by conventional means? The cosmos contains approximately 2 trillion galaxies, each containing hundreds of billions of stars. The number of planets is incomprehensible. The variety of environments, the range of temperatures, densities, chemical compositions, magnetic field strengths, radiation environments, is staggering. Some of those environments might harbor life. Some of that life might be intelligent. Some of that intelligence might have had billions of years more than us to develop technology. In that enormous, ancient, varied cosmos, what is waiting to be found? What has already been found by minds we have not yet encountered? What knowledge, what art, what philosophy, what science, what ways of being conscious in the universe exist out there, unknown to us, separated from us only by the vast distances that a wormhole could, in principle, eliminate? This is not a question that physics can currently answer. But it is a question that physics has made more urgent and more real than at any previous point in human history. Because physics has shown us that the universe is not necessarily as inaccessible as it looks. The cosmos is large, but it is not necessarily unreachable. The silence between the stars may not be permanent, and the loneliness of our little world, this pale blue dot floating in an ocean of night, may not be the final word on the human condition. The science of wormholes is, at its deepest level, a science of possibility. It is physics pushing at the boundary of what exists, what is accessible, what is knowable. It is mathematics revealing that the apparent constraints of space and time are not walls but membranes, permeable in principle, traversable in theory, potentially crossable in practice. It is the universe showing us, in the language of equations and experiments, that it is larger than we think, more connected than we perceive, and more open to exploration than we have dared to imagine. And in that revelation, there is something that goes beyond physics. There is something that speaks to the deepest human need, the need to know, to explore, to cross thresholds, to discover what lies beyond the horizon. The wormhole is, in a sense, the ultimate horizon. It is the point at which the known world ends and something genuinely new begins. And the fact that physics says it might be real, that the equations of Einstein, confirmed by a century of experiment, allow it, even require it in certain contexts, makes it the most powerful horizon in the history of human imagination. Not imagined, allowed, not fictional, theoretical, not impossible, just hard. And we have always been good at doing hard things when we understood why they were worth doing. The fabric of space-time is not inert. It is not a passive backdrop against which events unfold. It is a dynamic, living, responsive medium that bends and stretches and folds and connects and vibrates. And within that medium, there are doors. Doors described by mathematics, hinted at by experiments, hunted by telescopes and quantum computers and gravitational wave detectors. Doors that, if they exist and if they can be opened, would transform the human species from prisoners of a single star into citizens of a universe. The 11 facts about wormholes that we have explored today are 11 windows into this truth. The Einstein-Rosen bridge, hidden in the first exact solution to Einstein's equations. The traversable wormhole, requiring exotic matter with negative energy density. And negative energy is real, demonstrated by the Casimir effect. The inevitable connection between traversable wormholes and time travel, emerging directly from the physics of time dilation. The visual appearance of a wormhole, a sphere, a window onto another sky, beautiful and terrifying in equal measure. The ER equals EPR conjecture, identifying wormholes with quantum entanglement and suggesting that space-time is woven from quantum connections. The 2022 quantum computer experiment, the closest anyone has come to probing wormhole physics experimentally. The quantum foam at the Planck scale, where microscopic wormholes appear and disappear constantly, potentially constituting the very fabric of space-time. The wormhole as the solution to the black hole information paradox, connecting the interior of black holes to the exterior through quantum geometry. The possibility of interuniversal wormholes, connecting our universe to other universes in the multiverse. The growing experimental program to detect natural wormholes, using the Event Horizon Telescope, gravitational wave detectors, and future instruments. And finally, the 11th fact, the most extraordinary of all, that the universe, in its quantum gravitational reality, may be not a collection of isolated regions separated by vast distances, but a fundamentally, profoundly, necessarily connected web, in which wormholes are not exotic exceptions but the very threads of the weaving. 11 facts, each one real, each one sourced in the work of living physicists at the world's leading institutions, each one pointing toward the same extraordinary conclusion, that the universe is not as we thought, that space is not empty and time is not fixed and distance is not absolute and the cosmos is not closed. The universe is open in ways that our ancestors could not have imagined and our descendants may one day cross. The wormhole is not a fantasy. It is a forecast. And the day it moves from mathematics to engineering will be the day that everything changes. So the next time you step outside on a clear night and look up at the stars, those ancient, distant points of light, scattered across the incomprehensible depths of the cosmos, remember what you know now. Remember that somewhere in that darkness, or perhaps just beneath its apparent surface, the fabric of space-time may be folded. That the vast distances you perceive may conceal connections you cannot see. That the universe may be, at its most fundamental level, not the lonely expanse it appears, but a network of geometric threads, woven from quantum correlations, braided into wormholes, connecting the far reaches of reality in ways that make the word universe, one world, not a metaphor but a literal truth. The universe is one, and perhaps one day we will walk it all.